And this is where I think we come in. So we set out, I said this a long time ago when I started this. It took a long time to do it. And it's still basically the only way to do it. This is a very big chemical. And these pretty ribbons you see have lots and lots and lots of atoms. A hydrogen atom weighs 1 Dalton. This thing weighs 77,500 Daltons. It's called lactoperoxidase. You make it in your saliva, and you secrete it into your mouth. And it then picks up hydrogen peroxide, this little wee molecule, 34 Daltons, and activates it to disinfect your mouth, kill bacteria and all sorts of other things. Now the problem with this thing is it's just too big to commercialize, although people have certainly tried with things like it. But if we could just get a small molecule mimic of that, we would be able to do lots of things. And we were able to get such small molecule mimics. We call them TAML, a registered trademark to Carnegie Mellon activators. The molecular weight's about 500 compared with 40,000 to 250,000. And so they've been known since the 19th century. I would say a large amount of federal dollars in this country as well in all other countries have gone to the chemists who have tried to mimic them. So I'll blow my horn a little bit here. We took a very unusual approach, which I'll explain to you as follows. The active site of these enzymes, just one atom, and it tends to be the active site so often in these enzymes. It's an iron atom, you know, a little piece of steel in there, but at one atom level. And the molecule that's being activated, the hydrogen peroxide, ends up interacting with that iron. But you will have cut your hand and put peroxide on, I'm pretty sure, most of you. Some of you may be too young to have done that. And you'll see the bubbles. And if you leave it on, it hurts. And when it's all over, when you rinse it off, you'll see white stuff. Now what went on there is a different kind of chemistry with hydrogen peroxide. It releases a little molecular bomb called the hydroxyl radical. It's very wasteful. The oxygen bubbles are wasted hydrogen peroxide, but it works well in that scenario. It disinfects your flesh, it cauterizes your flesh, and does the job it's supposed to do. That is no good for most technologies, even although we sometimes use it, because it's very wasteful of the peroxide. The enzymes don't work with the kind of chemistry that does. They do it very differently. And to make them work that way, you have to make the iron decide it's going to use the peroxide the way the enzymes do. And to do that, and this may seem a little arcane, you have to squeeze electron density at the iron. And that's what we really are just wrapping iron atoms up in straitjackets of negative charge. And if you achieve that, what will happen is this. When you put this thing in water, this is a water molecule, oxygen's red, hydrogen's white, H2O, it'll pick up 2 water molecules. But it's designed, and it does indeed work, for the waters to fall off easily, and the hydrogen peroxide that has 2 oxygens binds to it, and then that decomposes to throw away a water molecule, HOH, and leaves an oxygen atom. And that is now the reactive species. That's what happens in the enzyme. Very selective, doesn't waste hydrogen peroxide. So the question is, could we do this? The problem is, if you saw the little flash of flame there, when you put the peroxide on, it goes and burns a hole in the ligand, because this is fire chemistry in water. This is oxidation, oxidizing things in water. And the stuff in the middle, all the stuff, there's a whole lot of atoms in between these key binding atoms, is burnable, and it just burns itself. And once it starts the burning, it blows to bits, and you're back to the chemistry you don't want. Well, how we were able to design this to over 15 years to actually get the catalyst is as following. There's your iron atom. Intellectually, we'll do it. We surround it with atoms that we think will work for the job. The blue ones are nitrogen, the red ones are oxygen. And then we tie them to the metal, and we tie them together. And then this grey stuff we play around with to try to make it work. And after about 6 years with that motif, we couldn't get it to work. It kept falling off. The oxygen would let go with the iron, and then the whole thing would just fall off. So we handcuffed those up together by changing it to nitrogen, which allows you to complete the ring. And then we started changing the things on. And over the period of time, we would change different parts of it to get it to function differently, always analysing how it was working. We just couldn't get it to work for 15 years. We were so close. And eventually figured out that that thing was burning, that piece of the molecule. It doesn't really matter what it was. But once we knew that, we were able to change it to something a little bit different. And then we had wonderful catalysts. And then once we got the catalysts that would actually work, we could go on and change them some more. And once you have these catalysts, you're very happy. You go and design and develop them further. You study how they work, and you study their applications. So at the same time, environmental health sciences and endocrine disruption was developing, and eventually Pete became a great friend. And the one thing I don't want to do is produce any more endocrine disruptors. So we're busily figuring out, well, how do you know that something's an endocrine disruptor or not? Because that is an incredibly difficult scientific question. And the only way, this emphasizes the thing about green chemistry that makes it so hard, but also so incredibly rewarding. Chemists tend to dig down into a specialization and come very deep at one or other thing. But to get there, the process of refining down, they lose sight of all the other things. To do green chemistry and sustainability, you can't do that. You've got to know about environmental health sciences and all of these other things. But you know what? If you're a scientist, you just can't be superficial.